one more time. So today we'll be talking about the classifications of, I'm going to call them quote unquote integrals. Okay. And the reason is because we've gone through two-ish different kinds of problems so far. Okay. So first let's recall what integrals are, how they behave, all that good stuff. Okay. So let's say you have some function f of x, right? And you derive it, right? If you derive it, suppose you're going in this direction, right? Derivations go here, and you get f prime of x, right? And the relationship between here and here is that this function is a slope equation, or yeah, slope formula, or equation of this function, right? And then so on and so forth. You can keep going that direction, right? But if you underive, right, if you go this direction, you might end up with something that looks like this, f of x, where f prime x is equal to little f of x, right? We discussed that. Here, we'll do that, right? But as we said, right, there are so many f of x, big f's, where if you derive it, you get little f. There's infinitely many, in fact, right? So an example, let's say little f of x is equal to 2x, right? Big f of x could totally equal x squared, or x squared plus 1, or x squared plus 2, or x squared plus pi squared. There's an uncountable many numbers of big f of x, right? And so that's why when we talk about big f of x, just in this form right here, right? This is called the antiderivative. Antiderivative, right? Okay. What if we don't want an infinitely many number of things? We want one very specific thing. We just don't know what that specific thing is, right? Well, option number 2 is you say the integral from a to c of little f of x dx, right? And what you end up with is, you still have to use this big f of x. You have f of c, oops, minus f of a. And this will usually, unless like I give you variables up here and here, right? This will usually give you a number. Okay. Mysterious third option. Mysterious third option is, what if I don't give you bounds, right? If I just say the integral of f of x dx, right? Oh, and as a side note, this can be called the definite integral, right? So you have this, right? You don't have a lower upper bound, right? But you certainly don't want antiderivative either. That's okay. Because this, you can call it as big F of x. This is very important, my friends. Plus c. Or if the c confuses you because we use c here, you can also call it plus k. I don't really care. Okay. Okay. Now, this is the antiderivative because you're underiving, but it's still kind of loosey-goosey, right? This is called the definite integral because you're anti-deriving, and then you're applying bounds because you know what those bounds definitely are. Definite integrals, right? This third option is an integral. You did integrate, right? If you integrate, then you have to have some semblance of, normalcy. but you don't know what your bounds are, right? And this is what we call an indefinite integral. Not to be confused with improper. We'll get to that later, maybe. Okay? So, do you see the vision? Good. If you don't, run it back. All right. So, loosely speaking, an indefinite integral of little f of x is just the integral sign of f of x is usually dx, and this is going to equal big F of x, the antiderivative, plus c, or k. Both are fine. All right? So those are the three categories. I personally don't care for antiderivatives. I only like them slash teach them because they're useful here and here. I think they're a little silly. All right. Okay. Question is, what now? Especially, what if we want to solve for k, right? What if we want to solve for k? That's okay. That's easy because I'm about to teach you guys what? An intermediate value problem. No, sorry, not intermediate. I'm going to teach you guys how initial value problems work. Okay. So 9 out of 10 times, here's what's going to happen. 1, you get an f of x. 2, you want a big f of x, right? Such that f of x passes through some point x naught comma y naught. Okay? Right? Because this can be anything. Right? Big f of x can be anything, but big f of x that passes through x naught comma y naught, an initial value, is a very, very specific kind of thing. All right? So from there, you say, take indefinite of little f of x for solve for k using x naught comma y naught. That's it. Okay. And of course, if I say, oh, just take the indefinite integral, like if I just say, like, oh, f of x and dx, you just calculate it out and then you say whatever f of x, big F of x is plus k. Because I didn't tell you what k needs to do. Okay? And it's very easy. It behaves the exact same way, like, whatchamacallit. It behaves the exact same way, like solving for the x, or sorry, the y-intercept of a linear function is because, like, fundamentally, right, you end up with big F of x plus k. If this is equal to 0 and k is a constant of integration is what they call it, that k, it really is just the y-intercept, friends. That is to say, g of x, you could call it, I'm calling it differently so we don't get confused, is equal to the integral of f of x dx, which is equal to the antiderivative plus some constant. Okay? And then you can call this like g of x as well, so you don't confuse yourselves. Yay. Anyway, okay, let's do an example. Let's say I want let little f of x equal to an easy one, 2x. And I want, right? Okay, you want your point your g of x passed through here. Okay, so you want g of 0 is equal to 1. Okay, well, I know that g of x is equal to x squared plus k. I know g of 0 is equal to, well, we plug 0 into here, right? 0 squared plus k. We also know we want the output to equal 1. This means 0 plus k is equal to 1. K is equal to 1, which means we have g of x is equal to x squared plus 1. That's it. Let's do a harder one. Let f of x equal, now I don't know how nice this will work, okay? 1/3, actually, no. Let's do 4x cubed. G of x is equal to the indefinite integral of f of x dx, and g of 1 is equal to, let's do 16. Okay. First, we're going to integrate f of x, which is going to equal the integral of 4x cubed dx, which is going to equal x to the 4th plus k, right? And again, we know this is equal to g of x. 2, g of 1 is equal to 16, so we have g of 1 is equal to 1 to the 4th plus k, which is equal to 16, right? Plug the 1 into here, which means plug it into here because, and then we're trying to solve for k, so we don't know what it is, and we know this whole thing has to equal 16, because that's what's given to us, right? Easy. Then you say, oh, 1 to the 4th is 1. 1 plus k is equal to 16. K is equal to 15. That means you get g of x is equal to x to the 4th plus 16. That's it. Initial value problems. Woo. Thank you for your attention. I will see you next time.